Can you hear me? Okay, great. I'll just wait a few more minutes to see if anyone else is gonna join in. Guess we can start at Berkeley time. Okay, I guess then it seems like people have stopped joining at a rapid rate. So I'll get started. So I have a couple of practice problems regarding like reaction kinetics, etc., that I thought we could go through. So it'll require some audience participation. So I hope we can talk through these problems together so I'm not just here talking to myself because it does feel weird like everyone has told me. All right, so here, oh, now I'm having the same problem that Jeff does, is it doesn't advance normally. There we go, okay. So here is the first question. So we want to try and rationalize the ordering of the ligands in the trans effect series. So does anyone want to start us off as to why this is the order that we get? Okay, you all can hear me still, right? Just making sure. Okay, cool. Well, then I guess I can just give you the answers. Yeah, so the ordering of the ligands in this series is a combination of two effects. So it's like the trans influence and the trans effect. So basically it's the combo of the trans influence, which is the sigma effect. So since both, if you're considering a like platinum complex where you have T as the trans effect ligand and X as the departing ligand, both T and X in the sigma effect use the px squared minus y squared and the px orbitals to bond to the metal. So if the platinum trans director sigma bonding is strong, then those metal orbitals will be more involved in the bonding between that ligand and the platinum, which weakens the extent that those orbitals can be involved in bonding with the departing ligand on the opposite side of the metal. So that just like weakens the bond with the departing ligand. And then the pi effect is when um, um, the trans influencing ligand is a pi acceptor. So that removes electron density from the platinum center. And so the entrance of a fifth ligand is more favorable because the platinum center is more electron deficient. So therefore it wants another ligand. Also, you can utilize the dx squared minus y squared, the dxz and the dyz orbitals to pi bond in a trigonal bipyramidal transition state. So that lowers the energy of the transition state and decreases the activation energy for the ligand substitution to occur. So you get, if you combine these two effects, then you can see that the strongest trans-labelizing ligands are strong pi acceptors and strong sigma donors, and the weakest trans-labelizing ligands are weak sigma donors and pi donors. Does anyone have any questions about that?
So, does it work to like also associate like softness and hardness with this? Like, I have written in my notes that basically like softer species, which are more like along the lines of pi acceptors, are more translabelizing. Is that like reasonable to say, or is it like a trap?
So I guess thinking about like each individual ligand is probably the best bet, but like those I guess general statements are not super, are not unhelpful. So like our soft ligands are going to be ones with like lots of like iodine, so large electron clouds. And so those are going to sort of be like the weakest translabelizing ligands. So you're, I mean, you have to just like consider how the orbitals are interacting with the metal center. So like soft ligands are going to be making the metal center more electron rich. Therefore, it's going to like minimize the trans effect and stuff like that. So I guess you can try and use generalizations like that to guide you in your thinking, but just thinking about like the specifics of how the orbitals of each ligand are interacting with the metal is the best idea.
Okay, thank you.
Cool. Any other questions, or I can move on to the next slide. Okay, so now we're going to consider some questions regarding a square planar complex, ML4 reacting with an incoming ligand X. So first we want to identify what the elementary reaction steps would be. So does anyone know what like the general reaction coordinate would look like in terms of how the incoming ligand interacts with the metal center?
Is it like an associative process for square planar?
Yeah, that's right. So you're just having the incoming ligand forming a square pyramidal complex, and then after the departing ligand L will leave. So then you're left with an ML3X compound. So I guess the next question would be, what are the point groups of the reactant, intermediate, and the product? So our first one is square planar. So what is the point group for square planar complexes with the same ligand, where there's 4 of the same ligand on the metal? Oh, yeah, cool. D4H. That is correct. And what about for the square pyramidal intermediate? Yeah, that's right. It's C4V. And then lastly, after the ligand L leaves, what will the ML3X square planar? So it's square planar, but it doesn't have the same, it has 3 of the same ligands and 1 friend ligand. What would that point group be? It's not D2H, but you are right that the highest order rotation axis is 2. But you wouldn't have 2 like perpendicular, yeah, right, C2V, because you don't have the 2 perpendicular twofold rotation axes for that one. So yeah, in this case, like the twofold rotation axis goes through that the like X ligand. and the L ligand that's trans to that, and it just rotates around. Cool. So I think I'm just gonna show the reaction coordinate for this reaction would look like this, where there is some stabilization that's like afforded when the ligand binds, but that's still a pretty high energy intermediate, so therefore it'll proceed to lose the L-type ligand. Yeah. All right. So going back to our questions. So now that we know what the reaction coordinate diagram looks like, how does this reaction coordinate diagram change when L is a strong sigma donor? So we're thinking back to the things we discussed with the first question. So what effect does a strong sigma donor have on the ligand that's trans to it?
Trans effects?
Yeah, sure. But how does that change the reaction coordinate diagram? Like where would then the where would the reactants be like in terms of like an energy level? So like if you had a weak sigma donor versus a strong sigma donor, where would the complex with weak sigma donor fall relative in energy to that of one with a strong sigma donor? Is that
As the strong sigma donor has a higher activation energy.
That's close. So the strong sigma donor will just be higher in energy, like the starting complex, because the strong sigma donation and trans effects weakens the stability of like the bonding between the metal and the ligands for that complex. So that starting complex will just overall be higher in energy. So if let's say this is like the energy level of a weak sigma donor, then a strong sigma donor would cause the energy of the starting complex to be up here. But that would then overall lower the activation energy to the ligand substitution. Therefore, like, so that's just like an energy coordinate, reaction coordinate diagram explanation of like the trans effect. So by having a strong sigma donor, you're lowering the activation energy to the ligand substitution. Does that make sense?
Yes.
Okay, cool. Any questions about that? All right, and then our last question for this guy. I see in the chat, the question is, why is the bond weakened? So that's just going back to our first explanation for the sigma effect. So in this case, you have only the way that we were discussing it is like all the ligands are the same. We just have 4 of the same type. But so that's all of those ligands are going to be competing for the like bonding via these dx squared and the dx squared minus y squared and the px orbitals. So that's just overall going to like weaken the bonding that each ligand can have with the metal center. And so more of the sigma bonding, or sorry, when the sigma bonding is strong, the metal orbitals are like more tied up in that interaction. So then in that case of like a metal with 4 of the same type of ligand, if all the ligands are strong or strong sigma donors, then like all of the bonds are relatively weak in that between the metal and the ligand in that complex. Does that answer your question? Okay, cool. Okay, and so finally, how does the reaction coordinate diagram change if L is a strong pi acceptor? Oh, JK, and that is the answer. Anyway, so the energy of the reaction intermediate is lowered due to the trans effect, and this is because the trans effect decreases charge on the metal center, which lowers the activation energy. Yeah, sure. I can upload the review session recording. Yeah. Yeah, no problem. All right. So lastly, all right, here is a reaction. There are 2 isomers of this platinum amino chloride diamino dichloride complex, and they can react with excess thiourea. One product is platinum with 4 thiourea ligands, and the other one is platinum with 2 amino ligands and 2 thiourea ligands. And so each of these complexes comes from either the cis or the trans version of this starting platinum diamino dichloro complex. So let's try and identify the isomers, reactants, and products. So we'll just talk it out instead of drawing it, but try and rationalize which starting isomer leads to which product. So let's start out by identifying whether like the general translabelizing effects of like of the amino ligand versus chloride or ammonia. Sorry, it's been a long day. So which one is a stronger trans labelizing ligand, ammonia or chlorine?
Is it chlorine?
Yeah, that's correct. So that's because ammonia is like a sigma donor, but like not super strong, and chlorine is a pretty good pi donor. So I'll just give you guys the fact that thiourea is a pretty strong trans labelizer. So I guess cool. Let's start out with trying to figure out which isomer would form this platinum thiourea complex. Does anyone have any ideas as to how that complex could be formed from which isomer?
Sorry, I don't want to talk too much, but if no one else is talking, then my guess is it would be like the isomer in which the ammonia are cis to each other and the chlorines are cis to each other.
Hmm.
Um, should I explain why I think this?
Yeah, please.
So I would think that um, first there'd be the chlorine would be translabelizing, so the ammonia would kind of like get substituted by the thiourea,
Hmm.
and then the thiourea would be more translabelizing than the chlorine. So then the chlorine would be substituted with thiourea. And if it happens with both sides, then you get 4 substitutions. I don't know.
Yeah, I think yeah, you're on the right track. Yeah, what do I have said? That the chlorides would be initially replaced by the thiourea, but I think that's wrong. Yeah, sorry, I think this my answer key is incorrect, but yeah, so you're right. So in the chlorides would yeah, labelize the leaving of the ammonia ligands, which would be replaced by thiourea, and then after that, the thiourea would labelize the leaving of the chlorines and replacement by additional thioureas. Yeah, that's right. So then the other complex is formed by the trans isomer of the platinum platinum yeah, I guess diammonia dichloro complex. So in this complex, the first chloride gets displaced by the trans influence of the other chloride ligand. And so then next, the strong trans effect of the thiourea leads to replacement of the second chloride ligand. So you end up with 2 thioureas trans to one another in the place where those 2 chlorides were. Does that make sense to everyone? I'll have to change the answer to the first one. Anyway, so this is all I've got in terms of questions for today. But I was thinking we could just use the rest of the time to like office hours. So let me know if you have any questions about things we've been discussing in class or the problem set.
Hi, I have a question.
Mm-hmm.
So in class, this was from lecture 13. Professors said something about 2 competing pathways for the associative mechanism. And so I was just confused on what he meant by the 2 different pathways.
Okay, let me see. Is there a slide that he had this on?
I don't know if it's in there's a specific slide, but I have it in my notes.
Sure.
So I don't.
I'm not quite sure what if he means that like it's competing between like associative interchange or just pure associative. Um, I'm not sure if that's what he means by two competing pathways. Yeah, sorry, I'm not quite sure.
Okay, that's fine. Thank you.
Yeah.
I had a question also.
Mm-hmm.
So I was wondering, there was a